All right, guys, welcome to the first of really all of our instructional videos. What these will do is if you can't make it to class because of quarantine and absence, etc., this will provide you a way to make up the instruction. It'll be almost identical to what I do in class. So please take notes on this. Pause the video as you see necessary to make sure you're getting things written down. If something isn't making sense, well, you can't physically raise your hand. Pause the video, shoot me an email, and I'll be able to help you out. Okay, so this specifically will be over 2.1. And you might be wondering, well, why are we starting in chapter 2? We're just starting the year. The reason is because of the pandemic, we're skipping over chapter 1. It should be chapter 1 is all review from 8th grade math. If you would like to look at that on your own, brush up on things, make sure you're confident on the topics covered there, you can read that in your book. But for now, we will not be going through it. Instead, we're going to jump into chapter 2. And chapter 2 is going to be all about solving equations. What are equations? Well, it's when one thing equals something else. If we look at that word equation, the root of the word is equal. Okay, so we're going to have something equaling something else. And really, this is what algebra is famous for. Y equals 3x plus 2, or 3x minus 2 equals 5x plus 4, solve for x. If you had an older sibling who's taken algebra, if you ask them to recount what algebra is about, this is probably one of the more predominant things they would remember. And so that's what we're going to explore here in chapter 2. And really, this would be the first thing I would write down. The big idea here, though, what do I have to know? What do I need to remember? What is done to one side must be done to the other. Remember, our goal is solving equations in which the root of the word is equal. The root of the word is equal. And to keep things equal, again, you can imagine the balance here. You've probably worked with one in science before. We have to do the same thing to both sides, right? If this scale is balanced and I add 5 pounds to it, well, the scale is going to tip in the one direction. So to balance it out, I would also have to add 5 pounds to the other side. The same is true with equations. We are going to be manipulating equations, which we'll get into in a bit why we're manipulating equations. But if we make a change, a manipulation to an equation, to keep it equal, you must do the same or an equivalent manipulation on the other side. And again, we're going to dig into that here. But first, let's start with this principle. You see them here in orange and blue. If A equals B, then A plus C equals B plus C when A, B, and C are real numbers, and consequently also if A equals B, then A minus C and it equals B minus C when A, B, and C are real numbers. And these are some principles of equality, okay? And where you might not understand these, but I'm sure if I wrote out a number example, let's say I have 7 and 7, or let's not say 7, let's say 3 plus 4, right? This is a true mathematical statement. 7 equals 3 plus 4. We all know this is true. Well, if I add 4 to this left side, I now have a left side equal to 11. And now no longer, this is not a true equation, right? This would no longer be true. 11 does not equal 3 plus 4. So what would I also have to do? Sorry, that was meant to be a 4. Well, I'd also have to add 4 to the right side. If I wanted to add for some reason, and again, we'll dig into the reasons why in a bit. If I wanted to add 4 to the right side, I wanted to add 4 to the left side, I would also have to add 4 to the right side for the equation to stay equal. So again, I'd add 4 to the right side, and what that would end up giving me is 11. Okay? So the idea is if I have two things that are equal, you can see them here in green, 7 equals 3 plus 4. If I add something to one side, I am okay, the equation is still true if I add the same thing to the other side. And the same could be said for subtraction, right? If I subtracted 4 from the left side, if I subtract 4 from the right side, the equations will still be equal. Now you might be wondering, okay, well, that's all fine and well. What's the point? Well, this principle is going to help us solve equations for variables. Specifically, we're going to use it with this idea of inverse operations. You see, what we're not going to be looking at is 7 equals 3 plus 4. What we're going to be looking at instead is 7 equals x minus 5. And what we're going to want to do is we're going to want to isolate the x variable here. We're going to want to isolate it so we can figure out what it is. And one of the ways we do that is these things called inverse operations. Inverse operations are going to help us move numbers around so the variable is by itself. This helps us find the solution. But in doing that, the principle we'll keep in mind is what we do to one side, we must also do to the other. So let's go ahead and try an example here. 7 equals x minus 5. Again, what we're rolling around in our brain right now is this idea of equality. What I do to one side, I have to do to another. But my goal here is to figure out what x is. Okay, x is a variable that stands for some number or numbers in some cases. And we want to find the value for x that makes this true. Now, you might be sitting there with Mr. Carter. I know what it is. I can just think about what should go in for x and find out what I need to plug in for x so that when I subtract 5, I get 7. I can do that. And that's fine, and that's great. But what happens when we get 3x minus 15x plus 6 equals 4? That's a little more complicated to think through and figure out what the numbers should be for x. So let me give you a method that, whether it's this complex problem in blue or a very simple equation here in black, will work every time. And the idea is based on inverse operations. What we're going to do is we're going to isolate the variable so we can find out what it is. It's a whole lot easier to tell what the variable is when it's by itself. What do I mean by that? Well, ideally, we will transition from x minus 5 equals 7 to x equals something. In other words, x is by itself. If we get the variable alone on one side, it will just say what it is. So how do we do that? Well, we're going to use inverse operations. And first, before we dive into using them, let's talk about what they are. Inverse operations. Inverse operations means if I do it, if I do one, it is the opposite of one that's already occurring. Again, the word inverse shouldn't be new. You'll see multiplication is the opposite of division. They're inverse operations because if I multiply something by 2 and then I divide it by 2, that division by 2 counteracts the multiplication by 2. If you have 5 apples and I give you 3, but then take away 3, you can see how the adding 3 and subtracting 3 are opposites. They counteract one another. Okay, inverse operations. It's when you either multiply to cancel out dividing or subtract to cancel out addition, whatever you may have. Okay, so let's go back to our x minus 5 equals 7 example. How are we going to combine these ideas we've thrown around? Well, I want to figure out what x is. And I know that I need to get x by itself, because if I get x by itself, then what's going to happen is it'll just say what the value for x is. So how am I going to get x by itself? Well, the x is currently being subtracted by 5. Okay, we're taking away 5 from the x. If x is, again, a pile of apples, I'm taking away 5 from it. Well, I want to know how many apples in total I have. So what is the opposite of taking away 5? Well, the opposite of taking away 5 would be adding 5. Okay, now you go, why are you, if you're taking away 5, then why are you adding 5? Well, if I do this, the two will counteract each other and will cancel out. What do I mean by cancel out? Well, if I would write this out side by side, if I had x minus 5, and then I said, well, I'm going to add 5 to that. Well, when we look at this, we see that what? Minus 5 plus 5, hey, that's just 0. Well, what's x plus 0? Just x. So by using an inverse operation, what I can do is I can get the variable by itself. Well, if you might go, okay, you add 5, okay, x is by itself, that's cool. Well, remember, we can't just add 5 into equations. Otherwise, that scale becomes unbalanced. So what do we need to do? Well, if I add 5 to the left side, I also must add 5 to the right side. Now what you do is you just simplify. We saw here that when I add 5 to the left side, I'm just left with x. And if I add 5 to the right side, what's 7 plus 5? 12. So what I see here is that x minus 5 equals 7. I use inverse operations to get x by itself. And when I do that, I find that x equals 12. By using inverse operations and changing the equation, by changing, I mean changing how it looks, not changing the fundamental properties of it. What I end up with is I find out that x equals 12. Now, the cool thing about this is, how do you check your work? Well, algebra, you usually can check your work by plugging your answer in back into the original. Remember, this is an equation. These two sides are equal. So whatever value or values I get for x, if I plug them in, should make both sides equal. So let's check it. What happens when I plug 12 in for x? Well, I have 12 minus 5 equals 7. I can simplify the left side to be 7. 12 minus 5 is 7. And look, I get 7 equals 7. Hey, when I plug in 12 for x, both sides are equal. The equation is true. Thus, x equals 12. Okay, that might seem a bit lengthy and maybe a bit confusing, but I think if we do a couple more examples, it'll make sense. Again, if you're stuck right now and something I'm saying isn't making sense, go ahead and pause the video, shoot me an email. But otherwise, we'll just keep doing some examples. Let's add the equation x minus 3 equals negative 8. And what I'm trying to do here is I want to identify what value of x makes this equation true. Well, again, I could, because it's a fairly simple equation, I could just try and think about it. But let's not do that because, again, we understand there could be more complex equations out there. Let's instead try and use the math we've learned with these inverse operations. And your little chart here, if you've forgotten what the inverse operations are. Addition is the opposite of subtraction, and multiplication is the opposite of division. So let's use some inverse operations here. Well, I want to get x by itself. And we saw last time, hey, if I could get those numbers on the left side to zero out, I'll just be left with an x. I want to have x all by itself. Well, I have that minus 3 there. So how can I get that to zero out? In other words, you could think about it. What could I put on the left side that will combine with this negative 3 to give me 0? Well, again, going back to inverse operations, we have a minus sign here. So we know, well, it probably should be a plus. And if I am taking away 3 apples, what would be the opposite of me taking away 3 apples? Well, it would be me adding 3 apples. So what am I going to do? I'm going to add 3 to this left side. And again, you can see kind of the math written out here. Negative 3 plus 3 is 0. X plus 0 is just x. So if I add 3 to the left side, hey, that positive 3 that I'm adding in will cancel out with the negative 3. And I'm just going to be left with x, which is what I want. I want x by itself so I can see what it is. Now, what I will do to one side, though, I can't just magically add 3's in. That scale will become unbalanced then. So what I do to one side, I must also do to the other. Well, negative 8 plus 3, a number plus another number. Negative 8 plus 3, I get negative 5. So what I see here is that x equals negative 5. X equals negative 5. Again, how could I check my work? How could I make sure, hey, did I do this quite right? Again, we've got an equation going on here. So if I'm doing this properly, both sides should be equal. In other words, if the solution I got for x is correct, it should make both sides of those equations equal. So I plug in negative 5 for x. And I want to see if these sides are equal. Well, if you check it in a calculator, negative 5 take away 3 does give you negative 8. So both sides are equal. And thus, our solution of x equals negative 5 is correct. Okay? Now is a good checkpoint to see if you're kind of picking up what we are doing. So why don't you go ahead in your notes and pause the video right now and try this on... Actually, positive 2, sorry. Try this on your own. See if you're really grasping the concept we're doing. Give this one a shot. See if you can figure out what m is by yourself. And not just by guessing, but by doing the math. Okay, hopefully at this point you have paused the video and given it a shot. Now check your work with mine. We have m minus 2 equals 10. Well, we have 10 being taken away from m, whatever m is, we're trying to figure it out. So what would be the opposite of taking away 10? Well, the opposite would be adding 10. Again, I'm doing this to get m by itself because I have negative 10 plus 10 that will zero out. It'll become 0, and I'll just be left with m on the left side. But what I do to one side, I must also do to the other. So I also add 10 to the right side. The minus 10 and the positive 10, again, when you add those together, are 0. So I'm just left with m. On the right side, I have 2 plus 10, which gives me 12. So I find out that m equals 12. And again, how could I check my work? Well, let's plug it in, see if both sides are equal. When I plug in 12 for m, on the left side I have 12 minus 10, which is 2. And hey, we got 2 equals 2. That looks pretty good to me. They're both equal. Thus, our solution for m, the variable m, there should be a 12. Okay, try one more of these just to make sure we really got it. Again, I would recommend pausing the video and trying this one on your own. Okay, hopefully you tried it. Check your work with mine. I'm trying to figure out what A is, what A stands for, what is a solution for the variable A. So what I'm going to do is, I want to get A by itself. So to get A by itself, I will subtract 4.2 from both sides. Again, I'm doing that because there's a positive 4.2. So if I want to zero it out, so to speak, if I want to get A by itself, I must take away 4.2 from the left side. But what I do to one side, I must do to the other. So I subtract 4.2 from both sides. On the left side, I'm just left with A because 4.2 minus 4.2 is just 0. 15 minus 4.2, that is 10.8. A equals 10.8, therefore. And if I would plug that back in for A, I'm going to I check my work. I could plug 10.8 back in for A and see that it indeed, when added to 4.2, does give me 15. Okay, let's try a slightly different type of problem now. Let's go ahead and try and find the variable R here. Let's identify what R is. And if you think you got a handle on this, or this is review for you, go ahead and try it on your own. But if it is not review for you, that's okay. Just hang with me. So how are we going to solve this type of equation? In other words, how are we going to find out what the variable stands for? Well, when we look at this, what we see is the R is being divided by 4. And again, we have the same goal. Get the variable by itself on one side so we can identify what it is. Okay? So how are we going to get it by itself? Well, again, let's think about what is happening to the variable. We have the letter R. What's happening to it? Well, the R is being divided by 4. The R is being divided by 4. So if the R is being divided by 4, I want to get it by itself, what do I need to do? Well, we talked about this concept of inverse operations, doing the opposite to kind of cancel something out. So what I notice here is if the R is being divided by 4, and I want to get the R by itself, I don't want that divided by 4 to be there. What I'm going to do is I'm going to multiply by 4. Why would I multiply by 4? What's the logic there? We saw earlier that adding and subtracting, when you add and subtract identical numbers, they become 0, leaving the variable by itself. Why am I multiplying here? Well, if we look at this, what we have here is 4 times R over 4. Well, when we have a whole number times a fraction, as hopefully you learned in middle school, you multiply this whole number, acts like a fraction over 1. When we have two fractions multiplied together, we multiply top by top, bottom by bottom. So I'd end up with 4R over 4. And what we see here is we know if we have any number, you might have even seen it in the previous step, any number divided by the exact same number just becomes 1. So when I observe 4 divided by 4, I know that that is just 1. So I'm left with 1R. Well, what is 1 times anything? Well, 1 times anything is just itself. In other words, what I'm showing you here is that if something is divided by something and I multiply by that same thing, you are just going to be left with the variable. I'm dividing the R by 4 by multiplying by 4. The 4's nullify. In other words, when you have something divided by the exact same thing, it becomes 1. Well, 1 by anything is just itself, so you're left with the variable. This is why multiplication and division are deemed inverse operations. Okay, they cancel each other out. So the R is being divided by 4, so I multiply by 4, which will cancel out the 4's, leaving me with just R. Well, I can't just multiply one side by 4. Again, we saw earlier what you do to one side, you must do to the other. So I must also multiply the right side by 4, which gives me 8. So by using inverse operations and getting R by itself, I found that R equals 8. Again, if you're unsure, we at our base level had an equation. And so if it's an equation, both sides should be equal. So let's see if when we plug in 8 for R, since we're saying R is 8, if it makes the equation true. Are both sides equal? Well, when we do, of course, we see that 8 divided by 4, we can simplify that to 2. We get 2 equals 2. That's true. Therefore, we can justify that our answer of R equals 8 is correct. The big point being, this does not just apply inverse operations and getting variables by itself. Does not just apply to addition and subtraction. It also applies to multiplication and division. So let's try another example. Let's do 4c equals minus 36. 4c equals minus 36. Well, again, what I'm going to identify or observe here is what is happening to the c, okay? I want to get the c by itself. What is stopping me, so to speak? What's on the same side as the c? Well, when I look at this, what I see is 4 times c equals negative 36. That 4 is being multiplied by the c. The 4 is being multiplied by the c. So what I'm going to do is I'm going to, if it's being multiplied, I know that the inverse operations tell me if I am multiplying something by 4, I'm quadrupling it. If I divide by 4, that will cancel out the multiplication by 4 and leave me with just my variable. But I can't just do that to one side. I must also do it to the other. Negative 36 divided by 4 is negative 9. So when you divide both sides by 4, you get c equals negative 9. Again, checking my work. Let's see if 4 times negative 9 equals negative 36. Well, I do 4 times negative 9, I get negative 36. That does, of course, equal negative 36. Both sides are equal. The scale is balanced. Thus, my answer that c must be negative 9 is indeed true. Okay, so let's look at this final example together. We have 3/4 of r equals 12. 3/4 r equals 12. And you might be tempted to look at this and say, well, the r is being divided, so we should multiply by 3/4. And what might make you think there's a division happening here is because of the fraction sign. But we saw earlier the problem was r over 4 equals 2. The r over 4 equals 2 is an example of division occurring because the r is being divided by the 4. We can clearly see here the r is over the 4. But we don't have that exact same situation happening in 3/4 r equals 12. The r is not in the numerator of the fraction, right? What we don't see is the r in the numerator there. It's not in the top like it is on r over 4. What's actually happening here, because the r is not physically a part of that fraction, is the r is being multiplied by 3/4. If the r is not in the fraction and we don't see a sign in between the 3/4 and the r, like a positive or a minus sign indicating addition and subtraction, what's happening is the 3/4 is being multiplied by the r. The 3/4 is being multiplied by the r. So if the 3/4 is multiplied by the r, and again, there are numerous ways to do this. You could rewrite this and say, well, if 3/4 is being multiplied by r, we could write this as r over 1, and you could get 3r over 4, and you go, but now it is in the fraction. I would say, yes, it is in the fraction, so there is a division happening there. And of course, we would then multiply by the 4, and we would go on and solve it that way. Again, that's an alternate way of thinking about it. And you could do it that way. But I think the simpler way to do it is we acknowledge that the 3/4 is being multiplied by the r. And so if the 3/4 is being multiplied by the r, according to the logic we've been following with inverse operations, we should then divide by 3/4, right? If I am multiplying by 3/4, the opposite would be dividing by 3/4. And that, of course, as we've seen before, when you divide by the same thing you're multiplying by, you're just left with your variable. And we're on our way to solving it, but where you're probably stuck is you go, oh man, 12 divided by 3/4. Ooh, divided by fractions. That's not nice. But it's actually not as bad as you would think. You see, when you divide by fractions, and if you don't know this mnemonic, you'll see it on my chalkboard. When dividing fractions, it does not need to be a big deal. What we do when we divide by fractions is we actually end up multiplying. We flip the fraction and we multiply. It's called the reciprocal. You flip the fraction and multiply by the reciprocal. Again, if you want to know why that happens or what the math is behind that process, I'm not going to go into detail about it in this video. You hopefully learned about it in middle school, but if you want to learn the detail, I'll sit down with you and talk with you about it sometime. Okay, but anyway, 12 divided by 3/4, because we divided the left side by 3/4, we must also divide the right by 3/4. So we do 12 divided by 3/4. Well, 12 divided by 3/4 is the same thing as multiplying 12 by 4/3. Again, when dividing fractions, don't ask why, flip the second, flip the denominator of the fraction, and multiply. In other words, take your 12 here, your numerator of your fraction, and multiply it by the reciprocal of the denominator. Like you see here. Well, when we do that, we again saw earlier with fractions being multiplied or by whole numbers, we write the whole number as a fraction over 1. We have two fractions being multiplied. 12 times 4 is 48. Multiply the numerators, multiply the denominators, and I do 48 divided by 3, and I get 16. So a little more complicated because we had to do some dividing of fractions, but again, still the same process. Get the variable by itself via inverse operations. And we got r equals 16. Now, especially in a more complex problem like this, where we can't just see it eye to eye or at face value off the bat that 16 would go in for r and make the equation true, this is a good one to especially check our work. So if r is indeed 16, then if I multiply it by 3/4, it should equal 12. In other words, if I plug it in for r in my original equation, it should make that original equation true. So I multiply it by 3/4 in the calculator, and you do indeed get 12. You also could have done it by hand and done 16 times 3, got 48, divided that by 4, and gotten 12. Okay, so again, hopefully what you're walking away with is you have a beginning understanding of how we get variables by themselves in equations. We do that using the inverse operations. And the reason we do that is because by getting the variable by itself, we can identify what it is. Guys, thanks for watching. As always, let me know what questions you have.